Here is a picture of a Maxwell-Boltzmann distribution. What that shows is the number of particles that are traveling at a certain speed. Let's look at this very broad distribution down here. It's not very tall, but it's very broad. What it says is at this particular speed there are that many particles that are moving at that speed. If we go to a higher speed, like right here, we see that more particles are moving at that speed. If we go to a very high speed, we can see that there aren't very many particles that are moving at that speed. It's a lot like cars on an interstate. Most cars on the interstate are going at somewhere around 75 miles an hour. That would be something like this. There are quite a few people going about 75. There are fewer people who are going about 70. There are a few more who are going closer to 80. But there aren't very many people who are going 60. There aren't very many people who are going 100. That's what this distribution is trying to show. And this one here represents various gases at the same temperature and pressure. The peak for each of these curves is called the RMS, or root mean square speed. That we can consider to be like the best average speed of all these particles in a sample. Each of these different gases, each one is a different type of gas, they all have a different RMS speed. You can see that for the distribution that is fairly short, this one has the highest average speed. Now, there are some of the particles in that sample that are traveling relatively slowly. But on average, they travel faster than do the particles of either the tallest distribution or the medium one. Which means that if these are at the same temperature and the same pressure, then they're going to have the same average kinetic energy, and if on average one of them is moving the fastest, then that must be the one with the least mass. And the one on average is traveling the slowest would be the most massive gas. If we have a similar distribution, but this time it's for samples of the same type of gas at the same pressure and various temperatures, and that leads us to the conclusion that if these are the same type of gas, each particle has the same mass, so the ones that are moving the fastest must be the warmest. And the ones that on average are moving the slowest, we measure that as the coldest gas. The equation for the RMS speed of a gas is given here. It's symbolized by a letter U, and it's equal to the square root of 3RT divided by M, where R is the universal gas constant, and here it must be the 8.314 variety. It has other values that are used often in other gas law applications, but for this equation it must be this one. Furthermore, the molar mass that is used in this equation must be in kilograms, and I point that out because often in chemistry we simply calculate grams from the periodic table, but when you're using this equation you have to be very careful to use 8.314 for R, and you also have to find the molar mass in kilograms. Well, we know from physics that for any particle of any size, the kinetic energy is equal to 1/2 mv squared, where the m must be in kilograms, the speed must be in meters per second, and that gives us kinetic energy in joules. So that equation applies for massive objects like rockets, or also very, very tiny objects like gas particles. So let's find the RMS speed of chlorine gas at 80 degrees Celsius. So there's our equation. We're going to convert the temperature into Kelvin because we can't do any calculations with gas laws unless we have the temperature in Kelvin. We know what this T term is. We know what R is because it's a constant, 8.314. Now we just have to figure out what's the molar mass. Chlorine is diatomic, so it has the formula Cl2, and from the periodic table You can see I've taken a snapshot of chlorine's spot. Cl2 would have a molar mass of 70.9 grams. But the m in this equation must be in kilograms. So we're not going to put 70.9 under this square root sign. We're going to put 0.0709. Now it's just a matter of plug and chug. We've got the correct temperature in there in Kelvin. We got the correct value of R. We got the correct molar mass in kilograms, 352. And what do we measure speed with in the SI system? Meters per second. Now let's find the kinetic energy of one typical chlorine gas molecule at this temperature. Of course, they're not all moving at exactly the same speed, but if we had to guess what kinetic energy the typical one would have, this is how we would do it. We know the equation for kinetic energy. We know that the typical chlorine gas molecule should be traveling at about 352 meters per second. So we know the V term. Now we just have to figure out the M term in kilograms. One Cl2 molecule has a mass of 70.9 AMUs. We know the conversion between AMUs and grams, and in order to use that kinetic energy equation, we can't have grams, we have to have kilograms, which gives us that many kilograms for the mass. And now we're ready to put those numbers into our calculator. 1/2 mass in kilograms, speed in meters per second, squared. We're only squaring the speed now, not the other stuff. And that gives us a fairly tiny number because after all we're only talking one molecule of chlorine and the unit for energy is joules. Let's summarize. The Maxwell-Boltzmann distribution provides information about how many gas particles have what speed under various conditions. For a given gas, the Rms speed increases and the distribution broadens as temperature increases. For a given temperature, Rms speed increases and the distribution broadens with decreasing particle mass. The Rms speed of a gas, U, is given by that equation in yellow, where R is equal to 8.314 joules per mole Kelvin, M is the molar mass in kilograms, and T is the temperature in Kelvin.